have exceptional pleasure to host two senior fellows, not just one, and that's extreme accomplishment for any enterprise, because there's, I don't know, among 30,000 people, engineers, there's only a small handful of senior fellows. First talk will be by Chandrakant Patel, who is chief engineer and, as I said, senior fellow at HP. Chandra, would you mind sharing your screen? Chandra will talk for about 30 minutes, then we'll switch to Ray, and then we'll open up for the panel. I please ask you to turn off the cameras during presentation. You can come back during the panel again.
Well, thank you, Dan. Are you able to see my presentation? And
yeah.
Am I good to go?
Yes.
Excellent. Well, first, it's a great pleasure to be invited, Dan. Thank you for inviting, and seeing all friends from HPE and lots of IEEE colleagues going back to all the way to ICDC and 2011 is a great pleasure indeed. And this is what actually makes us all very happy to be in this community in Silicon Valley. So in my talk today, I will articulate a cyber physical course ahead, and I will underscore that success here will necessitate operating at the crossroads of domain, data, and data sciences. I will start by looking at the socioeconomic ecological megatrends in a very abstracted way and contend that we are entering an age of value-driven innovations which are cyber-physical in nature. I will articulate an example, in this particular case, 3D art to part pipeline. The reason I chose to articulate that is because I just wrote an article in the National Academy of Engineering Bridge Journal, an essay on cyber physical integration. I thought that might stand as a good reference, so I chose that. And we'll close with the workforce needed to be successful in the cyber physical age. What I'm going to do is I'm going to leave the Q&A for the panel part, because the focus is going to be on the workforce, the way I end my talk. So I'll hope to do that. And if I miss any of your questions, please, I'm happy to take it offline. So I hope my slide advanced, Dejan. It should say megatrends and the rise of cyber physical systems.
That is correct.
Brilliant. So let's take a look at the socio-economic and ecological trends. And in doing so, oftentimes we see, so the picture you should see says supply demand. And oftentimes when people look at megatrends, socioeconomic megatrends, you see data after data, aging demography, this, that. It makes my head spin. So the way I look at megatrends, and I've been doing this for 5 years as the chief engineer, advising our executive leadership and the board on what ought to be our technology strategy in light of the megatrends. So the way I look at it is this one single abstracted view is something that we always did at HPE and something I've picked up with all the colleagues who are here. The way I think of megatrends is to look at the supply side and the demand side. On the demand side, I look at our fundamental needs at home, at work, on the go. Food, water, shelter, waste, transport, finance, training, all of these are fundamental needs. And thanks to internet, cyber physical security and privacy is also a fundamental need. So these fundamental needs are being met by a pool of supply side resources: power, water, waste, healthcare, cloud data centers. The socioeconomic ecological megatrends are a perturbation between supply and demand. So I won't go through all of them, but let's take one: aging demography. In Silicon Valley, in United States, indeed in the West, we have a challenge with aging demography. People who know how to run our infrastructure, build our civil infrastructure, run physical systems are retiring. My son is studying to be a cardiothoracic surgeon. There are 4,000 cardiothoracic surgeons in the country of 300 million. He won't even be a practicing cardiothoracic surgeon until he's 35. So people don't want to go into this field. There are much easier ways people perceive of making money. So there is a huge challenge of human capital, particularly in light of aging demography. So given that, the question that is asked of us is, how will we address that and what will be the role of technology? And my contention is It is time for value-driven systemic innovation in light of these megatrends. So, given the aging demography, what technologies will we use to address this? Could be one way to look at it. Similarly, what kind of technologies will we use in healthcare? And in so doing, we need to articulate the course of the future by looking at value-driven systemic innovations that matter to society. And looking at it, I think it's important to look at the trends as we have seen them. The 19th century was the machine age. It was an age of great domain depth. It was an age when here in Yosemite, we were just talking earlier, the Hetch Hetchy Reservoir was built by O'Shaughnessy that supplies pristine water to us in Silicon Valley. It was an age of steam engines, power utility. Then came the cyber age, the information age. The latter part of the 20th century was the rise of internet. The internet created a gigantic abstraction layer. We sat above the abstraction layer with our cell phones. It did a lot of good, but it also abstracted us away from great domain depth. We became very data-driven, very breadth. The technology breadth was largely data, collecting data, largely human-generated data, and there was tremendous growth in social media and e-commerce. Now comes the 21st century. The 21st century cyber-physical age is the integration of cyber and physical. The Tesla automobile being an example of a cyber-physical innovation. Then it's an age where we have to ask, let's go to that mega trend I talked about, aging demography. We recently had a customer who visited us. They manage railways. Their concern is people who run railways are retiring. So in cyber-physical age, the question then becomes, how will we build the operating technology and information technology systemic innovation, a cyber-physical innovation, that will enable this customer to utilize human capital better? So how can one person manage multiple trains? In this context, what is the role of VR and visual analytics, haptic holography? How will we collect data from the train and manage multiple physical infrastructure, whether it's trains, power plants, and the like? How will we use visual systems, VR, to train additional people? So that's the way we've been thinking about opportunities in the cyber-physical age. Recently, we introduced from HP a platform called Omnicept. The Omnicept platform is a VR solution where we have integrated sensors that will determine the cognitive load of a human being. Because we felt that not only do we see a rise of cyber-physical system, we are seeing a rise of cyber-physical human system. So consider this sketch. Let's assume it's a Tesla. And Tesla is not only making their cars, they're also making the trucks on their same assembly line. So now the assembly lines are flexible, configurable systems, very complex. So how can one person manage this complex system? One way we think this will happen is the VR systems will discern the cognitive load of the person to minimize errors and enable the person to seamlessly be integrated into physical systems. This is kind of the calibration of how we are thinking of value-driven innovations that matter to society. So when we think of VR, we just don't think of gaming. We think of how will we use it for training? How will we use it to manage physical systems? So that is how we are thinking. And that's how we approach megatrends. And in light of that, articulate variety of systemic solutions. I gave you one by way of example. So now let's go one deeper into what do we mean by cyber-physical system. Cyber-physical systems for us is an integration of operating technology and information technology. And security is cyber-physical security. So what do we mean by that? So let's go again to that Tesla example. So you should see a picture of Tesla automobile with a stack on the right. So my daughter works for Tesla. When she went to interview in 2014, like all parents, I keep a whiteboard in the family room. And I like to start with domain. So I said, well, you're interviewing for Tesla tomorrow. How do you size the motor in the car? Why is it an induction motor? How do you, so calculate the wind resistance, calculate the rolling friction, size the motor. What actuators would you put on the physical platform? What sensors will you put on the platform? Because your boss wants to autopilot the car. So let's start at the operating technologies layer, understand the physics of the system, understand the actuators, sensors. It goes back to the time when at HP we worked on in data centers and we talk of them as flexible configurable systems. So how do we put all the flexibility in the physical platform? And therein lies the need for domain understanding. Unlike a restaurant, where we could have recommendations come later, on a physical platform, we have to think ahead of time what actuators and sensors go in. And then we say, okay, I understand these are the kinds of data I'm collecting, and the machine-generated data must have context. It's not thumbs up, thumbs down. So how our domain understanding comes in on what sort of data and what context should be collected with data, the data format. How will we collect the data? What kind of knowledge discovery must take place? How will we close the loop on a policy-based control system? So when I turn on the autopilot, I'm setting a policy. How will we do that? How will we build the closed loop control system? So as you see, I started at physical. I ended up with data together with I integrated the operating technology with information technology. And so in her case, I said, you cannot go to the interview unless you understand everything from bottom to the top. This is the world we are entering. It's the world of hardware, software, co-design. And then above all, how do you keep it secure? So now what I want to do is go into yet another example. And this happens to be the area that I'm working on currently. It's the 3D additive manufacturing R2-part pipeline. And I'll go through this particular example of a cyber physical system. It's a very interesting one. In 3D, imagine I'm going to lift a car. So we are entering a world where I'm saying, I'm going to design the link when I need it, need-based provisioning. If I need to lift a car, I'll design the link, I'll send it to a 3D printer, it will print the part, and I'll use it to lift the car. So if you look at the value chain, it starts with the design, ends with the link. I need to make sure that the link is secure. Nobody has tampered with it. So cyber physical security comes in. And it's a proposition that is driven by the need to create a least joules workflow, where I build things when I need it, and it must work properly. This kind of part-to-part pipeline and this thinking really came into being recently. This is an article, a paper or commentary we wrote in Nature. And this was during COVID-19. There was a need to build medical devices, ventilator valves, swabs, isolation rooms. And in this context, when the need arose, the 3D part-to-part pipeline went into action to create everything from PPEs to medical devices to isolation rooms. We are entering an age where if I need a PPE, I ought to be able to scan my image at home and send it to, I should be able to send it and have it printed when I need it. So I accidentally hit and moved my slide. I'm going to go right back. Sorry. So this is the world I'm heading to. Here, success in 3D additive manufacturing necessitates a holistic perspective that starts at design, goes through device into the factory. And it's an integration of operating technology and information technology. It starts with domain theories, right? Mechanics of solids, mechanics of fluids. And that's what's needed to build a system. On top of that, we need to build it as a flexible, configurable system. Just like the Tesla, I need to put the actuators a priori. I need to understand the actuators, and more on this in a bit. Then I need to think in terms of the compute and communications. When I deploy these 3D print engines, 100 of them in a factory with visual systems that are scanning the powder bed, I'm not sending that data to the cloud. The computation will occur locally. So what does the micro data center look like? What will be the communication? If I use 5G telephony communication, the infrastructure that goes in there, how is the data connected? You need to think of computation and communication, not only at the data center level, but also the compute that goes inside the 3D print engine. Next level up is machine generated data. It's not thumbs up, thumbs down. If I were to take an image of the powder bed, so in 3D, we lay a powder bed, as you see in this detailed image, and in our case, in HP multi-jet fusion, we lay a powder bed, whether it's a polymer powder bed or in the case of, say, a polymer 3D print engine. We lay a powder bed, and then we jet a fusing agent in regions where we want to solidify. And that region is heated with fusion lamps, which results in solidification layer by layer and creation of a 3D object. In order to create an object that would be structurally sound to lift a car, for example, I have to make sure I build parts that will meet the structural requirements. So in order to do that, a lot goes in. I need to be collecting data, understand the temperature data. I might also be collecting visual data, scanning the powder bed. So if I'm scanning the powder bed, let's say I take an image of the powder bed and I send it to the cloud, it's meaningless. I need to have context. The context could be when I took that image, what was the mass flow of the agent that was being dispensed on the powder bed. Here's what the cyber physical stack looks like. This is a 3D print engine. Here's the detail of what the detail inside. Here's the part being built. So layers, drawing slices come in, and on top of the powder bed is this writing system, which is jetting the fusing agent and a detailing agent. Thousands and thousands of nozzles at 10 kilohertz. So imagine thousands of actuators at tens of kilohertz jetting agent. And right behind that is a fusion heater and an overall heater. In other words, the actuators are agents that I'm jetting and the heaters. So I need a controller that will determine how much agent I need to put and the amount of heat flow in order to create a part that works for me. So it's a very complex multi-input, multi-output control system. So Cullen, you go back to the time we worked on data centers, we had maybe 10,000 sensors, 600 actuators. Here we're talking about thousands and thousands of actuators. If I want to build a closed loop control system, I can't build the plant function. So I need to start with domain theories and come up with, collect the data and use machine learning to come up with the plant function to create a closed loop control system. This, folks, is the shape of things to come. And once again, it is underscoring machine generated data. If I'm taking the image, I need to have context, temperature, pressure, what is the amount of agent that was dispensed when I took the image, for example. All this requires domain knowledge. So that's just the box itself. In 3D, that's how we build the box. But there is a huge, yet another big opportunity. It's in systemic design. So if you look at how design has gone over the ages, during the machine age, we use a drafting table and we did multiple views to create an object. And that was machined out. In the cyber age, there were CAD tools. We used a variety of CAD tools, but we still thought at a part level. We thought of a physical part. But now with 3D additive manufacturing, we have the opportunity to do intent-based systemic design. What does that mean? Let's say that I am asked to design a cooling system for an electric car, for the batteries, for example, because without good cooling system, I will not get the life I expect from the battery. So in this context, my question is not about what part I'm designing, but what is the performance of the ensemble? How do I design the cooling loop so I minimize the pressure drop in the liquid cooling system, optimize the pump, and thereby get an efficient system? The opportunity with 3D is we can do contours that were hitherto not possible. So now the designer does not think in terms of parts. The designer thinks of how do I use 3D to create enhanced surface area, and think of it at a system level. The cold plate, the pipes, the heat exchanger. How do I make smooth area ratio changes to reduce pressure drop? And what's more, how do I design the impeller of the pump? You know, in the past, we used to, okay, go get the pump that is appropriate from a catalog. Now I can tune the pump impeller so that I am at the right pump efficiency, at the flow rate, the pressure drop I need. I can, in other words, I can do contours that are hitherto not possible. Therefore, I can do customized impeller design, which I could not do in the past, and do intent-based systemic design to be efficient. I talked about the box. I talked about design. The third big area in 3D, in the overall cyber-physical integration, is the creation of a digital factory. And I call it microgrids of digital factory. So once you design the box, you build the closed-loop control system, you use the domain knowledge, you build the design system to build parts. The only way we'll be successful is we need to build the factory, the data center. It was not the server during the data center days, it was the data center. That's what we said in the 90s. In 3D, it's not the one box, it's hundreds of boxes or tens of boxes or thousands of boxes going inside a building to act as a factory. Now, the digital factory is an integrated OT and IT. It has hundreds of boxes. By the way, one of those boxes is about 10 kilowatt. Our box is 10 kilowatt. 100 of them is a megawatt. Does it sound familiar to those of us who worked on the data center? Now I need to say, where will that 1 megawatt come from? I surely don't want to lose power in the middle of a job. How will I make sure I get reliable power? How will I manage? How will I make sure that it's a sustainable design? So I have to look at inflows, power flow. How will I do cooling and ventilation? How will I do resource? How will I do resource management? Raw material in, waste out. So there is the physical layout. And then how do I optimally lay out the machine? And then given a customer SLA, does it sound familiar? Given a customer SLA, create SLOs, allocate jobs to the machine. Sounds like servers, right? All we need is virtual machines now. So basically, hundreds of printers. When Dejan's job comes in, his job is critical. I will allocate a given, I'll put it in a given location, because where that part is made in an entire powder bed matters as well, depending on tolerances. So it becomes very critical on which machine, because each machine might be different as well. So huge opportunity in workload allocation among machines, given an SLA. In order to do that, you need an IT layer. Like I said, micro data center, 5G, MIMO. So you see, we are back to creating a local data center because the cloud won't be able to help. I always say, just send tweets to the cloud. You know, you can follow, tweets I can follow in real time, 148 characters. So send them to the cloud. All the analysis happens down in the factory. Then the other opportunity that comes up is, okay, if I can design the factory, is there an opportunity to make it net zero? And luckily at HP, many of us here who are on the call worked on this. It was net zero data center. So I said, well, let's just take a page from there and call it net zero digital manufacturing with a local supply microgrid. Now, why not put a 3D digital manufacturing plant at a dairy farm? Why don't you put it at Tillamook in Oregon, or say Clover up in Northern California? 2,000 dairy cows produce enough manure to generate a megawatt of power. That's sufficient to run 100 machines. So now think of microgrids of factories. Why do I need to have one large factory? Locate them at dairy farms, locate them at a hospital so that I can provision based on the need. And then that factory could run on sun, and I could shape the demand. Cullen, do you remember? We were shaping the demand based on the workload. So if Dejan's workload is important, I'll burn diesel for him. But if it is not important, I might wait for biogas from manure generation, or I might wait for the sun to come out. To do supply demand management, build a local microgrid and drive towards net zero. This is a page from our book in data centers. It's data centers all over again, but it requires deep domain knowledge. with that, let me close. I hope, in the short time I had, I made the case that in light of the socio-economic, ecological megatrends, it is time we did things that matter to society. It's the time of value-driven innovation. In order to succeed, we need full-stack contributors that go from domain data all the way up to data sciences. It's the rise of the T-shape. Individual with depth in one or many and depth in many other subjects. And success in the cyber-physical age necessitates depth in fundamentals, a multidisciplinary perspective, learned by doing systemic innovation through multidisciplinary collaborations. So this is an age where it's not thumbs up, thumbs down. You cannot possibly be successful without domain understanding. And maybe, Dejan, when we have time, I have 2 more sketches I want to share where I will articulate, when we talk about Silicon Valley and the future of Silicon Valley, I will articulate the importance of domain understanding. And I will even go out to say domain before data. So with that, I think I have about a couple of minutes left. I want to be respectful of time, and I'm going to stop here and take the questions maybe during the panel session so that my good friend, the brilliant Ray, can talk a little bit, give us insights into lasers. Something I used to get every day when I was working with him.
Thank you very much, Chandra. Would you mind stop sharing? Excellent. Ray, could you please start sharing? Everybody, we will, as Chandra said, we will ask the questions during the panel session. Ray, could you please unmute yourself also?
I'm unmuting, I'm starting my video, I'm sharing my screen, I am doing all of the things.
Like a true T-shaped person. Thank you.
Yeah, well, that T is upside down now, but who knows? Now, Chandrakant is clearly a visionary. He gave you a sweeping view of the future of cyber-physical systems and the social value of information and other technologies, essentially discussing for the 21st century, the next industrial revolution. Now, I will not do that. I'm going to shoot a lot lower, and I'm going to talk about, instead of megatrends, millitrends, short lasers a few millimeters long. And I only have 30 minutes. Trust me, I could bore you about this stuff for hours, but I'll try to teach you some laser physics, and I promise you it will not hurt much. The focus here today is trying to understand mode-locked lasers that we hope to be able to sell in the future, but we want to bring them to market much more quickly than has historically been possible in the laser industry. And that requires us to model these lasers with enough fidelity that we don't waste a lot of time doing things that won't work. And so with that in mind, let's focus in a little bit on exactly what the subject is going to be. So why bother building a laser model when you could just go into the lab, try a whole bunch of different things, and see what works? Well, we're going to talk today about a particular type of laser, a quantum dot comb laser, because it's critical to the way we are at labs approaching our research on silicon photonics. And the thing that's cool about these comb lasers is, instead of being like a telecom laser that costs $1,000 and only emits one wavelength at a time, these are lasers that can emit many wavelengths at a time out of just one package. And so we have these things called microring modulators that I'll show you a slow motion version of a bad one a little bit later in a movie that I hope actually works on Zoom. And the idea is to supply, this is like a laser power supply, put a whole bunch of data channels down a single waveguide or optical fiber that all come from one laser, modulate each of those independently. It's already spatially muxed onto the one waveguide, and then to use that to very cheaply supply a data center or an HPC setup. We imagine we'll need 1 million of these lasers in an exascale computer system that uses photonic interconnects. If they cost $1,000 a piece, that's $1 billion just for the lasers, and the computer system is supposed to cost 40% of that. So these lasers have got to be cheap. They have to be very, very reliable. The failure rate has to be incredibly low. Now, the first generation of these lasers, we're working with a company in Europe. They've spent 15 years doing R&D, and they're going to be separately packaged. They're not going to be part of the chips that we make that are silicon photonics enabled. We want to be able to bring these lasers into the package so that inside of the computer chip is everything that we need to transmit data optically over distances of a few centimeters to a few kilometers. And we really only have about 3 years to get our act together. We don't have 15 years. And it's an incredibly complex system, as we will learn soon. So the idea here is a QDCL is a quantum dot comb laser. We won't spend a lot of time talking about quantum dots today. Again, I could bore you for hours, but the idea is to come up with a way of engineering photonically enabled application-specific integrated circuits using lasers that have been tuned specifically for that application. And so these frequency comb lasers, you can vary the size, you can vary the material, you can vary the structure, you can vary the way you pump them, how much current you supply, precisely where they are located on top of the silicon waveguides, all sorts of other really complicated things. But what do we do to actually get them to work and be cheap and reliable? Well, I've written a bunch of notes. Those notes have been updated since then. But I was too lazy to update it, and you'll see why in a minute, because I have all these graphics that have to align with the words. But in order for me to explain this to you today, first I have to tell you what a laser is, including polarization, gain, and saturation. Then I have to explain to you what a longitudinal mode is, and then explain four-wave mixing and how the quantum dot comb laser actually works. Then I have to tell you what mode locking is, and that'll require that we discuss spatial hole burning and dispersion. And then what is a quantum dot? We won't actually get to that today. That's we have to save that for a later date. And then we'll ask, does it work? And what might be next? So now, pretend that we're in an art gallery. But instead of a beautiful painting, I'm going to show you a beautiful set of equations. And just like when you're looking at a painting in an art gallery, how you react to it is just as important as what the artist had in mind when he or she created the painting. And so we're just going to look at some highlights of these ridiculously complicated equations that describe what's going on in the laser that I've shown schematically in the upper right. It's a laser that is essentially a material in between a pair of mirrors, and the light circulates between the mirrors, and some of the light comes out. There's gain inside the laser. There's one of the mirrors in the laser is partially reflecting, and these ridiculously complicated coupled nonlinear partial differential equations describe how this laser behaves. The electric field is what we use to represent the light that comes out of the laser. The polarization, this parameter F, it's how the material responds to the field of light, the electric field as it propagates through the material. The gain is the amount of energy that's available inside the laser for us to extract and turn into useful light. And so we have a wave equation here for the electric field that's driven by the polarization. We have a partial differential equation that's driven by the electric field and the gain coupled together, very nonlinear. And then the gain evolves depending on how the electric field and the polarization couple together. This is a train wreck of complexity. And so we use a technique called finite difference time domain differential equation solvers in order to figure out what's going on. But there's an asterisk. The FDTD is dependent upon these two time parameters. Exactly what they are isn't important, but what does matter is that they are ridiculously short compared to the time that it takes the light to circulate around the laser cavity one time, and that's our clock. One round trip okay? And so in order to capture what's going on in this laser, we have to evolve the system forward in a ridiculously finely grained fashion so that we capture all the behavior. And so if you want to run, and I estimate about 1 million simulations in order to save us 10 years in designing and building these lasers, you do 1 day in a 1 CPU day per simulation. That's only 3,000 CPU years. Now, if we're thinking in a Zen fashion, patience can be a virtue. What's the rush? But in reality, that's not consistent with trying to get something to market in just a handful of years. And so we have to do a little better. First, we have to start by talking about what a laser is. And so when you think of a laser, you might think of a super duper laser pointer like the one on the right, but I also think of how to model a laser, what the physics of the laser are. And this is a book that I bought, well, 40 years ago. Yes, I am old, that describes how these lasers work in detail. I always go back to this book, this fundamental book, whenever I get stuck. But let's go to a really high level and try to understand what a laser is built out of. So every laser has a power supply, a source of energy that can pump that energy into the amplifier inside the laser. All right, and that amplifier is where that energy is stored. And then as we convert and store that energy, it provides gain for the electric field. We provide feedback for this amplifier using 2 mirrors that reflect light back towards the amplifier to pull more and more energy out of it. And then it's reasonable to ask, okay, fine, but where does the light come from in the first place? Through processes known as spontaneous and stimulated emission. And so imagine we're inside the amplifier. We've got a really simple-minded representation of the atom as just 2 energy levels separated by an energy E. We apply the pump, and that it adds energy to the system, and now the atom is in a higher energy state, the A level. We wait for an amount of time. That was the tau parallel number that I showed you in those differential equations, and out comes a photon. That's where the light comes from. But that isn't really enough, because then all you end up with is a neon tube, right? That's not a laser, but it sure does provide a lot of light. But let's go back and pump the atom up into the upper level, and then let's provide an additional photon. And before that spontaneous emission process has time to occur, that photon inspires the atom to emit another photon that's identical to the initial photon. And so this was a process that was proposed originally by Albert Einstein, or as us physicists call him, Big Al. Now, how does that actually help us make a laser? Now, laser, of course, is an acronym. It's not a noun, but I won't get into that today because it embarrasses the people who work for me. Let's imagine a laser as an athletic field with the 2 mirrors being end zones. And let's populate this field with players, with atoms, who are already pumped into the upper energy level. And now let's watch how this system evolves. Well, first in the upper right corner, we have 1 player down, and we've emitted a photon into the stands. It's not particularly useful. But then another player emits a photon that heads toward the mirror. Now, the mirror is partially reflecting, but that photon is reflected back onto the playing field at the same time that we lose another photon and another player in the lower left corner. This photon propagates along and then inspires another atom to emit an identical photon. And we see the medics have shown up in the upper right to repump that atom into the upper level. We have those 2 photons reaching the back mirror. They're reflected back onto the field. The bottom right atom emits a laser into the stands. We see stimulated emission of another photon using that atom in the middle. The medics are now taking care of the player on the lower left. We inspire another stimulated emission photon that propagates toward the mirrors. One of those photons leaks out of that partially transmitting mirror. 3 of the photons propagate back onto the field. We are now pumping 2 of the atoms back up into the excited energy level. We've inspired another stimulated emission. We've lost another player in the upper left. We are bringing the player on the bottom right back into the game, and you get the idea. We could go on like this until the laser's actually emitting a lot of light, but we'll be here all night. Now, there are a few other things that we have to know about how a laser works. The light can be absorbed and scattered by the background material or the waveguides. They can be transmitted by the mirrors, but all those processes are characterized by the photon lifetime, how much time the photon spends in the cavity. How hard do we have to pump? Well, depending on the units you're using, essentially the threshold that we have to pump the laser at before it lights up is inversely proportional to the photon lifetime. So the longer the photon stays in the cavity, the less energy we have to add to the amplifier. When the rate of stimulated emission equals the rate of spontaneous emission, that's called gain saturation. We're starting to lose the ability to repopulate all the players on the field because we're pulling energy out of the laser so rapidly. And then finally, what about stimulated absorption? You know, we could have a photon approach an atom in the lower state, gets pumped into the upper state, and that could be a real loss problem. But in fact, most lasers are what we would call ideal 4-level lasers. We add a ground state and an excited state. We pump the atom into the excited state. It rapidly drops the electron into the upper laser level where it sits there for a while. We see a stimulated emission event, and then rapidly that particle drops into the ground state. And so that's what a real laser actually looks like. I could have done this in the previous figure, but it would have been like trying to call a horse race telling you what each of the horse's legs did, which wouldn't have been very pleasant for anyone. Now, what is a mode? So now we know what a laser is. What's a mode? Well, let's use a violin as an example of spatially resonant modes. So we apply a spatial boundary condition to a continuous system. We clamp the ends of the violin string. Now we can construct a description of that violin string as a function of time using a Fourier expansion in space and time, or a series of harmonics. Now, each term in that series is a spatial mode with a particular resonant frequency, and we add up various amplitudes of those modes to get what's actually happening to the string, and that the amplitude of each of those modes gives us a map of the overtones, and this is why a piano doesn't sound the same as a violin or a guitar. The overtones are different, even though the central frequency, for example, is C. Now, here's an example of a resonant optical mode, and this is the movie. We'll see if it works. It's a real crowd pleaser if it works. We've got light propagating in at the top right corner. We have a microring resonator that light propagates past as we tune the laser so that the wavelength is an integer multiple of an integer multiple of the wavelength is equal to the circumference of that ring. It lights up. It has reached a resonance, and we'll need to use that in a little while to understand how the laser works. So we are going to represent the electric field as a collection of modes. So we're going to treat it like a violin string, and we'll set it aside. And this is exactly the formula that I use to model the electric field. We see it has a similar sinusoidal kind of time dependence. The round trip time, again, is the clock in this system. And we can see how the field evolves as a function of time for each of the values of Q, for each of the violin modes, for example. We can do the same thing with the spatial modes, although the UQs are a little more complicated. And we see a similar kind of behavior for the modes in between the two mirrors. In some cases, the field is large. In other cases, the field is small. And then we also allow our amplitude to change with time. Think of that as bowing the string. So it is like a violin, but we're bowing the string instead of just plucking it. Now, this is going to be a little technical, and I apologize in advance for that, but the four-wave mixing arises because of those complicated nonlinear equations I showed you earlier. So there's our representation of the electric field as a violin string. Remember, the the equation for how the gain evolves. It evolves in a particular way because the electric field interacts with itself, and that causes a mode where Q is equal to M interacts with a mode where Q is equal to N, and it causes to oscillate at a beat frequency between them. And so the gain is actually comprised of a whole bunch of beat modes or beat frequencies between the electric field modes. And in the same way, we have the electric field interacting with the gain to make the polarization wiggle like crazy. And in this case, it gets even more complicated. And what ends up happening is once you've factored all of this in, you see that now we've got an equation that describes how the electric field amplitude function, EQT, evolves depending on a sum of three of the fields in the cavity. And so this is how the different modes interact with each other. But you'll also know that the spatial coordinate Z doesn't appear anymore. And this is why this approach is so much faster. We've essentially reduced it to an ordinary differential equation. And some notes on modes. So is light a particle or a wave? Yes, it is. Rather than get into quantum philosophy, I'll just point out a few simple things. Think of the square of the electric field magnitude in between the two mirrors. Wherever that field is really large, you should think of that as, okay, the stimulated emission there is going to be really high. And whenever the field squared is low, the stimulated emission is going to be at a minimum. And the same thing is true as we tune the laser. So this is the brightness of that red ring as we tune the laser from left to right. And you see it goes through multiple modes. Every time we end up with an integer number of physical wavelengths that fits perfectly around the circumference, we get a maximum amount of light stored inside the resonator. It gets really bright and glows like crazy. Whoops. And so wherever the frequency is such that we have a very high amount of light inside the cavity, that's where we get maximum stimulated emission. And wherever it's low, we get minimum stimulated emission. And then finally, you can't get away with using really simple modes. This is one of the failures in the laser book that I showed you. What we had to do was come up with a new set of modes that actually correctly incorporated the boundary conditions. And that's one of the reasons that we were actually able to show that the laser will mode lock. There's also an effect called spatial hole burning, which allows the laser to run multi-mode. Now, in the case of quantum dots, there's a very limited amount of diffusion. The dots kind of stay where they are. And so we run into a situation where, remember gain saturation, where wherever the field is really high, we're going to get a lot of stimulated emission, but then that depopulates the atoms that are in that neck of the woods, in that neighborhood. And so we end up in a situation where we get heavy saturation in one place, and we get very low saturation in another place. So we have very little gain where the saturation is large, and a lot of gain still available when the saturation is small. And so that allows us to fit other wavelengths, allow other modes to actually sample the gain where the main mode, the Q equals 0 mode, is not sucking energy out of the atoms. And so this is how the system is able to run multi-mode. So I did something that does not come as second nature to me, and that I wrote Python code to operate the laser model. I didn't use Fortran, and I didn't use MATLAB. I went ahead and tried to learn Python, and I did it in an object-oriented fashion that allows me to choose different configurations of the laser, choose different material parameters, to choose exactly how I describe what was going on in the laser, and to incorporate dispersion and other effects, and that brings the whole model together and makes the whole thing relatively easy to use, I hope. And there's one other effect I haven't talked about that we actually have to include in order to understand what's going on in the laser, and that's dispersion. Now, what's dispersion? Well, the speed of light in any medium, like in glass, is speed of light in vacuum, c, divided by the refractive index of that material. That refractive index depends on the frequency of the light. And what that means is that if I start with a light signal that's comprised of multiple frequencies, as the light signal propagates, those frequencies separate in space and time. Now, this is a really big problem in fiber optics over very, very long distances, tens of kilometers. But our lasers are only a few millimeters long. So why is dispersion a factor? It causes phase shifts and time delays that we end up not being able to ignore because the dispersion is a factor of 100 to 1,000 times higher in these lasers than it is in an optical fiber. And so we're lucky. We need dispersion to mode lock the laser. And it turns out to be just the right amount. I mean, it's there and we're able to use it. And I'll briefly touch on that in a little bit. And so now it's a fair question. You put all this together, you run the code, does it work? Well, so far, I've done 400,000 simulations. It took about 6 CPU months. Now, if I had done that with an FDTD system, I'd have needed 1,200 CPU years. It actually would have been closer to 1,400, but I'm pretending that I'm using one of our exascale systems that we're selling the government. And you can see that I'm reproducing the kind of comb structures with many, many wavelengths. In fact, remember that shape because you'll see it again in the very next slide. But it produces a demonstration of multi-mode behavior that looks very much like what we see in our experiments. It includes a description of the phase relationship between each of those modes, which are required to get all of those modes to be stable and to go flying out one end of the laser in a fashion that we can use with our modulators. We've gone through and we've discovered the dispersion lock range by running huge sets of simulations in parallel. We varied cavity lengths, the output coupler reflectivity, the gain, and we've gotten all sorts of insight into the underlying physics of these lasers, including how the dispersion imprints itself. So a quadratic dispersion gives you this concave phase relationship between the modes. And the way that happens is described in a very straightforward way by our violin string model of the laser. And so what's missing? There's still a ton of work that has to be done in addition to another 500,000 simulations. We have a number of open questions. So there's a component in the laser called the saturable absorber. Didn't have time to talk about that today. When it's present, and even when it isn't, we see things like power splitting. Is there four-wave mixing in the saturable absorber? It's not really clear yet. Is there dispersion in the saturable absorber? We're working with a university in France to try to understand whether or not that's there. Why the hell is the dispersion just right to provide mode locking? Does the dispersion change as the laser mode locks so that it is just right? Is that one of the things the saturable absorber does? That's what we have to figure out in these next 600,000 simulations. And then what's the optimum value of the output coupler reflectivity? 10%, 50%, 90%? How many photons need to be reflected back in the cavity for this thing to operate with its peak efficiency? And I have to add a bunch of features. I'm working on a variety of things that have to be added to the model so that we're able to reproduce a wide enough spectrum of the behavior of these lasers in the wild. And I got to add more modes. You notice this shape here looks a lot like the set of modes that I showed you in the previous slide, except there's 200 of them here, and I showed you 40 in the previous slide. And so I still have a lot of work to do to demonstrate that at higher gains, you get this outrageously broad and relatively flat mode spectrum. And the code just has to go faster. We're currently doing about 1 simulation per CPU minute, and I think it needs to be 10x faster for us to meet our goals. And so we're talking to our HPC brethren to get some help on making the code go as fast as possible. And so thank you very much. I hope that I was able to teach you a little bit about laser physics, and I'm happy to take any questions before we get into the panel.
Thank you very much. Would you mind stop sharing?
Not at all.
Okay, thank you. So here's how we're going to do the rest of it. I'm going to ask a couple of questions of our panelists related to the Silicon Valley. And after that, I'll open up to everyone to ask either about Silicon Valley or about the individual technical topics. So I purposefully invited these two extreme technologists because one is living in Silicon Valley, Chandra. The other one opted not to live in Silicon Valley. So I'm just curious, what is your experience in living in or not living?
Dan, I'm going to let Ray go first, because just in case there were any laser questions, and then maybe he can take this on, because I think he asked people.
Okay.
Yeah, Ray, did you?
If anyone has a laser question, fire it away now. Otherwise, I'll explain why I'm living. Well, you see, I'm currently in my winter home in Mordor. So I'm not living in Silicon Valley right now. But if you have a laser question, let me know now, or we'll just move on. Going once, going twice.
I'll ask one, Ray. I'll ask one.
All right, shoot.
And this is very clever, and it would probably run 10 times faster if you didn't write it in Python.
I should have done assembly language.
What's the unsolved problem that you're hoping to fix here to change the world?
The problem is that we have got to be able to put on the order of 50 million frequency channels into an exascale system in order to move all the data through the switches from one node to another node while the exascale computation is being done.
And is this needed for El Capitan and Frontier, or is this for the next? No.
This is the next generation.
Okay.
All right. So think of the 10 exaflop machines, 100 exaflop machines. The interconnect is just not keeping up.
Gotcha.
And so the intent is to find a way. You can't provide 50 million wavelengths when each of those wavelengths costs $1,000 a piece. It's crazy. And so you have to be able to provide 50 wavelengths for $10, multiply that by 1 million, and then you can actually field the system. So without these comb lasers, there's no way to provide the level of optical interconnection we're going to need in these ridiculously large machines.
Brilliant. Thank you.
Any other question on silicon photonics or for Chandra?
Yeah, I just have one question on lasers. What's the expected power per mode that you're designing for?
Just a few dBm, a few milliwatts, not very much at all. The link budget is consistent with acceptable. We have avalanche photodiodes operating at 20 gigabits per second now that will count a bit if it sees a few thousand photons. And so even with a 20 dB end-to-end link budget, we're still okay with just a few milliwatts.
Great, thank you.
Correct. So Ray, it's about efficiency, right? So really the efficiency, power consumption is really the challenge, right? So
it is. And so one of the advantages you get with one laser and all of those wavelengths is whatever, and we don't need a huge amount of temperature control because we can handle modest drifts. And these quantum dot lasers also are able to operate at much higher temperatures. So you can set the band gap so that the optimum output power is achieved at 50 C, for example. But if you decide that you're going to go ahead and cool the package, you're cooling 50 wavelengths at a time, 50 lasers at a time for what used to be the cost of cooling one. And these lasers have wall plug efficiencies. So you pull electrons out of the wall and you turn them into photons. And the efficiency with which that whole process works is on the order of 15 to 20%, as opposed to 1% for a telecom laser. So that's a great question. The energy efficiency thing is a killer. And so you really have to be able to move a bit from end to end between two ports, for example, with just a few picojoules.
Use wire to water and this is wire to photon efficiency.
What's that? I'm sorry?
We always, in our, on the cooling side, we'll talk to wire to air and wire to water and
yes.
wire to photon.
That's exactly right. And we're always very honest about this. For us, the energy per bit to communicate includes everything. It doesn't just include the lasers, it includes the cooling, it includes everything else, all the electronics. And we start counting at, we used to call it latch to latch, but you move a bit off of a register and then you transport it and then you write it onto another register. And that's how we count it. So we're trying to be super duper honest about it. We don't just look at a part of the system, we look at the whole thing.
Sorry, there's one question on chat. Could you please share your viewpoint comparing Kerr comms versus mode law comms efficiency-wise?
I think that's a fantastic question. Currently, in order for a Kerr comb, for the rest of the gang here, you can take a micro ring system or a micro disc system and drive it with a single mode external laser. And through a variety of physical effects, you can generate a comb coming out of that nonlinear optical device. And the energy efficiency to a particular comb from that initial laser, which remember only has a 20% efficiency if you're lucky. So you start out in the bucket 20% with 20% efficiency, and then you try to convert the that energy into a comb. If you only have 50 to 100 comb lines, then the efficiency is usually quite low. You'll be lucky if you get 5% multiplied by that 20%. If you expand it to thousands of comb lines, then you can get the efficiency to start moving up towards 40 or 50%, but we can't use 1,000 lines. They're spaced so closely together that when you modulate one, it interferes with the signal that you're putting on the other. And so we need our lines to be on the order of 50 gigahertz apart, and about 100 of those, 50 to 100 of those, and that's our limit. And so in order to do that efficiently, we just have to go with a laser. But that was a great question. Thank you.
Okay, any other question by anyone? Or should we move to my Silicon Valley question? This was meant to be a controversial topic to attract more audience. But since I don't hear anything, Chandra, you want to start with your experience in living in Valley?
Yeah, I mean, here's how I see it. When I was a child growing up in India, I thought the US was a land of tinkerers. The pen pals, back then we wrote letters to our pen pals. And when our pen pals worked, mowed lawns, distributed papers, saved money, built radio control planes. And in India, we shared one copy of Resnick and Halliday among 10 people, and Americans, they were cool. They had a Western edition of Resnick and Halliday. So I felt like America was a land of tinkerers steeped in fundamentals growing up. It was not a naive perspective. It was absolutely spot on. When I joined the Valley, I was among Bill Hewlett, Dave Packard, Robert Noyce, Gordon Moore. I was in a valley of tinkerers. Today, I feel I live in a valley of abstraction. I've gone above the internet layer, kind of lost sight of what is below the abstraction layer. And so ideally, I would have started at the bottom and gone all the way up to the internet and understood what's going below the abstraction layer. But we are not there. So my concern is Whereas the internet has created this gigantic abstraction layer. It's a good thing. We can do a lot of things, but it's also a problem. And I'll close with this. My younger son wrote an essay. He's gone into civil engineering structures. And he wrote an essay to UCLA, UC Berkeley. And in his essay, he said, the internet has created a coffin for American innovation. That was his contention. And he says, the eastern span of the Oakland Bay Bridge was being built in Silicon Valley. Those of you who are not in Silicon Valley, this is a massive suspension bridge, a decade in the making, $11 billion. You could see the bridge come up from Treasure Island. My friends didn't even know the bridge was being built. With that, I rest my case. We have living in abstraction. We don't know the challenges from power, water, waste. We've lost sight of fundamentals. That's my concern. I don't want to be negative. I think for us to be successful, we need to traverse all the way from the bottom to top. So when Ray put up this fundamentals book, I was reminded of O-level physics by A.F. Abbott. That's what we use in 10th grade in India. When my daughter went to interview at Tesla, I was reminded of induction motor, and I was reminded of the textbook. So I think we somehow have lost sight of the fundamentals, and that's my concern with the Silicon Valley today.
Okay, thank you. What do you say, Ray?
I come at this from a slightly different direction. As usual, Chandrakant is thinking at a much richer, deeper, broader level than I am. I'm just profoundly narrow and selfish, and so I'll tell you how I ended up where I am. So I'm not actually a Mordor, that's Mount Rainier, Sunrise. We live in West Seattle now. To make a long story short, I was part of a company that HP bought in 1995, something like that. And I was absorbed into the grayscale printer division in Boise. And I was getting ready to leave HP because I didn't feel that was quite aligned with my interests. And I was starting to work on as a consultant on LIGO, the gravitational wave detectors that got built in Louisiana and Eastern Washington. And so I went to a conference at MIT for LIGO, and I called my wife and I said, you know, I've got an idea for starting another business. Now, she's a saint. She stood by and watched me go bankrupt 2 times, and entirely my fault because I am a terrible businessman, just incompetent to the core. And I said, I've got another idea for a small business. And she said, you know, while you've been working at HP, we've paid the mortgage 6 months in a row. So maybe don't do that. And I said, well, the only place I'd like to work at HP is at Labs, but that's in Silicon Valley. So you don't want to move to Silicon Valley, do you? And she said, no. Why don't you call them and find out if you could work in Silicon Valley but live in Seattle? And I said, they're not going to let me do that. That's stupid. And so she said, and I quote, call them now or don't get on the airplane to come home. So I said, okay, I'll give them a call, because at least I call them, nothing ventured, nothing gained. I called someone I knew at Labs. It was 2 o'clock in the afternoon on a Friday, and he he thought about it for about 5 minutes and called me back. I'm waiting at a payphone, called me back on the payphone, and he said, okay, I've got a plane ticket, come down on Monday and we'll talk. And so I went ahead and I did it, and it's been 27 years where I've worked in Silicon Valley but lived in Seattle. And initially, I was down there every other week for a week so that I could work in the lab when I got started. And then over the course of time, as I moved my way up the ladder and got shouldered aside by younger, smarter people who work for me, I was coming down for a few days every other week. We've got a lab in Santa Barbara as well, and I visit there. I think it's good for morale. that I'm not around much. My team appreciates the fact that it's easy to lose me. But I haven't found it difficult to interact with my team at a deep technical level, to work with them on the middling, idiotic, bureaucratic things that are typical of a large company, and be super productive. And I think that what COVID has taught us is that co-location is overrated if you aren't working in a lab. So I don't, to say is Silicon Valley dead or is Silicon Valley in trouble? Talk to those venture capital guys on Sand Hill Road and ask them if Silicon Valley is in trouble. Because if it's possible to start a company that is distributed across the country or the world with venture capital in Silicon Valley, and there are laboratories in Silicon Valley. I mean, I think one of the reasons it makes sense to have labs in Silicon Valley is just the talent pool is so amazing. Then it raises the question, what part of a company has to be in Silicon Valley in order to take advantage of that in the lab laser pool? Because I don't think you have to be co-located to take advantage of when you're not in the lab. I don't think it's critical that you be co-located. And so you'll notice I'm taking a super narrow view of your question, Dejan, whereas Chandrakant took a super broad view, which is typical because he's a big thinker and I'm a little thinker. But when I think of Silicon Valley as an institution, I think it's definitely going to change. Whether or not it's sustainable ecologically is a broad question that I'm not qualified to answer. But this notion of how people collaborate and how they are effective, I've gotten a lot more work done not traveling, not being at airports, not being on airplanes. Hell, when you go into any facility now in my company, our cubicles over the years have gone from being something you could spread out in to something that is smaller and smaller, to the point now where I need a shoehorn and a little grease to fit into a cubicle. The walls are getting lower and lower, so they're no longer really even 3D. I don't have a cubicle, I have a rectangle. And so your ability, it's sort of a default open office plan, which I do not believe in at all. And it seems to me that if you really want to think, you have to be able to get away from distractions and really focus. If you're going to do what Chandrakant is always recommending, and I believe fully, if you're going to think about fundamentals, it's very hard to do that in a noisy room.
Yeah. So Ray, I am the debate I don't want to get into with anybody is whether it's Silicon Valley dead or what's the future. It's the limitations, the challenges that I am really concerned about, particularly as I see my children and I see what's the future and what must be done. Therein lies the concern I have. So, and Dejan, if you don't mind, I'll share a sketch to kind of demonstrate an example, right? A daily example. So let me quickly share it. So let me see if you can do full screen here.
Control L. Yeah.
There you go. So you can see full screen.
Yeah. Yes.
So, I'll give you an example when I say domain before data. And I'll give you one example. In the 80s, there was a commercial on television. Ella Fitzgerald, the first lady of song, would sing and the wine glass would break. It was a company called Memorex. I used to work for Memorex. The commercial was, is it live or is it Memorex? So those of you at my age will remember that. And it was a prime time commercial. People knew why the wine glass broke. My contention is if I were to pick a person who's out of college and I said, can you tell me why the wine glass broke today? First of all, it will not be a prime time commercial. Secondly, if I were to ask somebody, they will say, you know what, Chandrakant, let me take data for 6 months and I'll do some correlation, I'll come back. Therein lies the problem. Everything is like oh, give me data, it's a bloody black box, I'll figure it out. That is a problem. In my opinion, it's domain before data. I'll give you another example. When Cullen and all of us were working on data centers, having the disk drive background, one day it occurred to me, and it was Mary Baker who had asked me to come and give a lecture at Usenet. I made this thing up. I was thinking, okay, these disk drives that go inside, these rotating disk drives with the arms that are accessing it, that go inside these servers, can a stimulus, a vibration from external stimulus cause resonant and create one of the modes, not a laser mode, but in this case, a mechanical mode that could cause a problem. So we extrapolated the fan speeds that need to be achieved in order to cool the servers as they became smaller. And we noticed that the fan blade passing frequency at 15,000 RPM happens to coincide with the arm frequency. And all I did was I took a disk drive apart, did first order calculation to figure out the natural frequency, one of the frequencies. In this case, the fundamental I thought was about 1,000 hertz. And I look at the fan blade passing frequency is 1,000 hertz. So we said there will be failures in the data centers when the fan is sitting at that speed, at that RPM. That problem occurred. And I saw a paper in which people said, we have problems with disk drives in data centers. We collected data for several months. There is no strong correlation to temperature, but we can't find the correlation. So this is the problem. Every time we bloody have to solve a problem, it's let me collect data and then we look for correlation. We should be worried about causation. And in this case, we wasted a lot of terabytes of data collection. Simple domain knowledge would have said why it would fail. So I think the problem we have in the Valley today is the domain knowledge does not have as much value as it did, whereas it was okay in the past, in the age of e-commerce and so on. In the cyber physical age, it matters. And so this is my concern. I'll give you one last example, the data discipline. Recently, with all these vaccines shipping, I see a lot of cloud companies saying, oh, we are tracking this. We'll track the supply chain. And when I see the person from the cloud company said, oh, yeah, we are going to keep it 78 below zero. 78 what? Rankine, Fahrenheit, Kelvin? Give me some context. If you are keeping it to minus 78 Fahrenheit, if it's Pfizer vaccine, might as well throw it out. So the discipline that goes with data is also important. All this comes from domain knowledge. And let me just stop right there. I think that is important. And this is why people like Ray, with this deep domain understanding are critical to us if we were to succeed in a world which is made of photonics and complex cyber physical systems.
See, if I had to summarize what Chandrakant just said, I would say that kids these days spend too much time thinking about artificial intelligence and not actually acquiring real intelligence.
That might be a good way to think about it. And
well,
that's
as complicated as I can think about it.
We have a number of questions from audience here. From Gene Freeman, we have a question. Are there places in the world not struggling with the abstraction issue?
I think there are. So there are some places which are not, but by and large, internet has reached everywhere and people are distracted with what is available about the abstraction layer. But there are places. If you go to companies that are hardcore, you go to John Deere and look at agriculture equipment they're making. They're making the tractors and they're connecting it to the network and they are building cyber physical systems. So the places where the full stack cyber physical systems are being built, I think they are not distracted, or at least a portion of it is not distracted. It's the people who are not going from bottom of the stack to the top of the stack that generally just operate above. I think they are distracted. That's a simple way of thinking about it.
Okay. Ray, you want to follow up, or I have another question for you?
No, go ahead.
From Tom Coughlin, the previous one was from Jim Freeman. So there are lots of maker and hacker groups in the Bay Area and elsewhere. So isn't there a counterculture of hands-on folks out there?
Yeah, actually, I think that's a great point. I think that, and in fact, I think it's a cause for considerable optimism. There are elementary schools now that are introducing the idea of tinkering with your hands, of learning how to program. In fact, the Raspberry Pi organizations now have, and Kirk Bresniker, if he's on the phone, I'm sure will speak much more eloquently about this than me. But I think it's just fascinating to see the number of elementary schools and high schools that are introducing kids to the kind of technology you can hold in your hands. There's electronic technology that you can put together like Lego blocks that do things that are even more remarkable than what regular Lego blocks are able to do. There does seem to be an effort to get kids to interact with the physical world using their head and their hands, and understanding how that this process of making, as you say, also has an IT component. And I think that's really exciting. And so when I think of cyber physical systems and the things that Chandrakant was talking earlier, in the kids who are, and one of the reasons I'm optimistic about the future, the kids who are doing this now are going to be asked to, and will have to tackle the problems that Chandrakant is talking about in the future. So we're a generation away of having all of our problems solved by kids who are smarter than I am.
Okay,
I answered that question in the chat. I completely agree with what Ray said. I just think that in light of the massive socioeconomic ecological trend, we really need to amplify that. And so some schools that have kind of walked away from it and teaching how to surf the web as opposed to metalworking, woodworking, ceramics, need to bring that back. So it's kind of let's return to some of that old school in a large way.
So in that context, there's a book that I read recently that I loved. Don't remember the author's name, but I think the title is Shop Class as Soulcraft. And it gets right to the heart of what Chandrakant was talking about.
Yeah, my son Devin, when he was in high school, he says, "Dad, I'm going to take a computer class." And I told him, "Look, anybody can be a mouse jockey. Why don't you learn metalworking or woodworking?" And so he went on to do bioengineering and became a doctor. And when he was doing research, he had to build a jig. His research was to agitate a wound area to increase blood flow and thereby do better healing. He went to the machine shop, built the jig, designed the jig, took it to the hospital. He's got HEPA clearance. So he's a doctor who is building things. So this is the kind of journey that you must undertake. You just can't be a doctor. You got to learn everything. So I'm glad I told him. Now he's gone into bioengineering. He's learned all kinds of data analytics tools, written many papers. But he would have missed the opportunity to learn metalworking and woodworking had I not advised him in that early age. That's my point.
Speaking of woodworking, here's a comment from John Zontag. All of the interesting challenges are about what you don't know. Domain is important, and so are friends with different perspectives. Comments?
I agree. That's why we live in Silicon Valley. I'd love to hear a dissenting opinion when I make fun of social media, for example.
I have no I'm on LinkedIn because I felt bad when our student interns who tried to link to me would complain that they couldn't find me on LinkedIn, but I don't do Twitter or any of these other things, which isn't what John was talking about, but I can't think of anything else to say because I agree with him completely.
I agree, 100%.
So question from Nirbhay Chaubi. Security is a major concern in cyber physical system. What are the mandatory components for securing communication, interconnecting cyber physical systems connected with IoT? What are the hardware and security challenges for cyber physical systems and Internet of Things IoT?
Did you want Ray to take this on?
No, this, believe me, this question is in your wheelhouse and not mine. So go for it.
So Nirbhay, this is exactly what I'm challenging our security team to do, is to take a holistic perspective on cyber physical security from end to end. And maybe the best way to answer this is what I've done is to kind of look at it across the board, like you said, from the domain understanding all the way to interconnect, including one of the areas that I told them is like, I'll give you one example. So if you look at cyber physical security, think of Stuxnet and the Iran centrifuge, which through, if you'll remember, a USB drive inserted into one of the computers would go on and attack and reduce the speed of the rotational speed of the centrifuge or something of that order. That's an example of a cyber physical breach. So let's calibrate on what are kinds of cyber physical breaches. And that's no different from what we did in data centers. Cullen will remember we had a building management system, and chances are Stuxnet, the centrifuge, also was using a Siemens BMS, and we were using a CMS. So somebody broke in, changed the speed, or changed some physical characteristic of the system. I think cyber physical system security starts with domain understanding as well. So if, for example, the centrifuge slows down, if you understood the physical relationship, you will say, that centrifuge better not slow down. So having a digital twin that mimics the performance of the physical system is the first place to start security in that context. So when you think of cyber physical security, you got to be much more holistic, not only look at communication systems and attack, but also performance characteristics of the physical system, and somehow having a model-based representation of that. So you could look at its functionality and say if it was under attack or not. It's a very big picture, lots of salient components in that, and it's a rich area where not very many papers exist. So Nirbhay, that may be a good place to kind of have in a security setting, talk about and have papers on that. And we are working on that, and when we can share it, I'll be happy to share it.
Okay, I somehow missed the comment by Apkar Dhaliwal to everyone. Chandra, I agree with your perspectives. Wait until people start to really deploy 5G FR2 millimeter wave networks on scale. There is not enough memory and backhaul to support those networks. We will most likely have to wait to 6G.
There's not enough energy and backhaul to support those networks. The backhaul is the problem. Like the fixed area networks were put in a long time ago. So that's why I often say, and I'm not an expert in communication, but when I put that sketch of a micro data center and I put the 5G cells, you know, I'm not as an expert like Ray, but I look at 5G, you know, 30 to 300 gigahertz millimeter scale. It's only going to travel about 100 meters in a humid environment. So, you know, I got cells, think of it in our building, with the fixed networks not growing. I think that 5G stays in a stadium or a building, and there is a micro data center, and only tweets go to the cloud. I'm one of those guys who say cloud 1.0 is good for tweets, like Katy Perry tweets at 148 characters. You could follow Katy Perry in real time. What is she going to do tonight? You know, what dinner she's going to have, what clothes we're going to have. But you can't follow a physical system. It's a bloody tragedy. Can't follow an airplane, the terabytes of data generated on an airplane or terabytes in a factory. So I think 5G will be awesome. It'll be localized with energy that can be used locally with a local microgrid of energy, but I don't see it going all the way back to the cloud data center as we know it. But I'm not an expert in that. That's just my view by sketching things out. Somebody who's a better expert at that could have a dissenting opinion.
And we have only one more minute for the last question from Gene Freeman, who is again bringing us to the most important things. How about those creating COVID vaccines? Do you see them suffering from the same limitations, lack of hands-on experience?
Quite the opposite in their case. I think when you read about the research that was done to come up with the current generation of vaccines that were looking at how the spikes on the virus behaved, and you read about mRNA and the other techniques that they use, it was pretty amazing. So the domain knowledge that they applied there was awesome.
Lots of data too, right?
Yes, but I think that when you look at molecular biology, it's very hard to take a data-only view of what's going on, and I think that I think it's very difficult, even though there's been some remarkable progress made in trying to use, you know, every time we say AI, what we really mean is machine learning, and I don't know why the hell we don't say ML, yeah. But to use machine learning techniques to try to discover underlying physical principles. And they've been toy demonstrations so far. But when you steer them in the right direction, you say, look, the correct answer has to be something like this, you can tackle some pretty amazing material science problems, for example. And I find that very inspiring, where the whole notion of AI as artificial intelligence, I don't think is useful. But the people in Silicon Valley and elsewhere who talk about AI as augmented intelligence, where it's data combined with the kind of, second order Taylor series based know-how that we are able to use in our brains to guide what is being done to this data. I think that's very powerful. And I think that the COVID vaccines are a beautiful example of that.
Yeah, I have to agree. I think that's a good way to close, is that it's at the intersection, it's at the crossroads of domain data and machine learning. And I think it was exactly the same thing when we were at HPE, when we could not, and Cullen is the master at this, we could not create a control system just because we could not create a physical model, but we had to start with an understanding, domain understanding, collect data to create that planned function. So it was a good example of domain going into machine-generated data and application of machine learning to create a model. And that's exactly very well eloquently described by Ray. That is what the Silicon Valley of tomorrow is in a nutshell, at the crossroads of domain, data, and data sciences.
Okay, gentlemen, and many ladies and other gentlemen who are still with us, thank you very much. Santa Clara Valley Corporate Liaison Program was really honored to have you. I personally always learned tremendous from Chandra and Ray, and I hope the audience has as well. Thanks, and this has been recorded. We'll put it up as soon as I manage to produce it, and hope to see you next time when we host the next talk.
Brilliant. Thanks, gentlemen.
Sure.
Bye.
See you, Chandrakant. See you, Dejan. Everyone else.
Bye.